Hello everybody, welcome back to another abstract algebra video. Today we will be proving that every subgroup of a cyclic group is cyclic. If you don't remember what a cyclic group is, we can remember that a group is cyclic if and only if it is generated by a single element. So what that means is I take a single element A together with its inverse and I'm able to recover every element in my group by taking powers of A along with its inverse. So what's the proof? So we're starting with the assumption that a given group is cyclic. So let G be a cyclic group. And further, let's say G is generated by an element A. These angle braces here mean generated. And A, we're saying, well, A is able to generate the entire group G. And now we want to show that a subgroup of G is also cyclic. So let H be a subgroup of G. This less than or equal than symbol, this means subgroup. And suppose H is not equal to the identity subgroup. And why do we take this assumption? Well, if H is equal to the identity subgroup, then H, let's rewrite this, is generated by E, the identity element, and we're done. So let's suppose that H is a subgroup and it's not just the identity subgroup. So there exists X in H such that X is not equal to the identity element. Now remember, H is a subgroup of G, so any element in H is also an element in G. So X in G implies that X is equal to A to the M for some integer M, or just some integer M. Now remember, we said G is generated by A, so any element of G can be written as some power of A. Okay, great. Now remember, the integers, the positive integers, the natural numbers, are bounded below by 0. So what this means is that we're able to pick a least element. So let M tilde be the smallest positive integer such that A to the M tilde is an element of H. Great. Now, let B in H be any other element. Once again, since B is in H, it's also an element of G. So B is equal to A to the N for some integer N. Now notice we have an integer N, an integer M tilde, so we're going to now apply the division algorithm to these two integers. So applying the division algorithm, to get N is equal to M tilde Q plus R for some Q and R integers. And here's the most important part. We know that we're dividing by M tilde, so R has to be strictly less than M tilde, our remainder. So 0 is less than or equal to R, strictly less than M tilde. So now we know that N is equal to this expression on the right. So this implies that A to the N, and remember this is our element in B in H, is equal to A to the M tilde Q plus R. And using exponent rules, this is the same thing as A to the M tilde to the power of Q times A to the R. Now remember, A to the N, this is an element of H. A to the M tilde, this is an element of H. So in particular, if I take it to the Qth power, This still is an H because H is closed. And also because H is a subgroup, it's closed under taking inverses. So I'm now going to apply the inverse of A to the M tilde to the Q on the left. So I get A to the M tilde to the minus Q, A to the N is equal to A to the R. Now, this is an element of H. A to the N is an element of H. Because H is a subgroup, it's closed under its binary operation. So this entire thing is an element of H. So this means that A to the R is an element of H. And we're almost done from here. So because A to the R is an H, we also know that M tilde is the smallest positive integer such that A to the M tilde is an H. Now notice R is always strictly less than M tilde. So the only way we don't get a contradiction is if R is equal to 0. So R equals 0. Otherwise, R is strictly less than M and positive, which contradicts the minimality of M tilde. But now we're saying R is equal to 0, so A to the 0 is just 1. So what does this mean? We said that B was equal to A to the N, which is the same thing as A to the M tilde Q plus 0, because we said R was 0. But now notice that we've written any arbitrary element of H as some power of A to the M tilde. So what this means is that H is generated by A to the M tilde, which implies that H is cyclic. And that's the proof. Thank you everyone for sticking around, and I will see you in the next video.